Hello, this is Phil Thomas from New Era Systems. Today I'm looking at a couple of power meters. If you've seen any of my prior videos, you'll see that I always use this Agilent E4418 because it really is very easy to use and it's very accurate. But we have several other power meters in the warehouse, considerably less expensive, but they still seem to work extremely well. Here's an example. This is the Boonton model 42B. It's an analog power meter, and so it takes a little bit of interpretation to know exactly what the output is. First, let's look at the test setup. I'm using a Comtech EF Data CDM 570L modem, generating a signal, 24 volt DC power supply, and also a 10 megahertz reference. And the amplifier, a buck in this particular case, is a 4 watt NJT, is coupled to a crossguide coupler at 14.25, has an offset of 40.16 dBm. That's important because it helps me when I calculate the output on the analog power meter. And of course, just behind it we have a dummy load to absorb any of the radiation being sent out by this block-up converter. First thing I'm going to do is to change the power input in several different steps and make a note using my trusty pen and paper of the recordings on the Agilent digital power meter. So let's start with -28. -28 is shown at 2.07. We're going to go to -27. Now we're down to 2.59. -26, 3.23. And finally we're going to do -25. And that's showing at 3.95. This buck is rated at 4 watts, so we're close to the recommended limit by the manufacturer NJT. Having got that far, I'm going to disconnect this power meter and I'm going to set up the Boonton. Now the only thing that I've done is to disconnect the power head from the Agilent and put the Boonton power head onto the crossguide coupler. I'm still running at -25, which according to the Agilent was 3.95 watts. And if we look at the scale on this, we're pretty accurate. We're almost exactly on 3.95. So now let's go ahead and test other areas in the range. I'm not going to step all the way through. I'm going to go to -25 to -27. So in fact I'm decreasing the power. On the Agilent, -27 was 2.59. And again, if we look closely at the scale on the Boonton, we can see it's just a tad over 2.5. So 2.6, yeah, I think we're pretty well on the money again. So now finally, let me move ahead to the lowest level that I did, and that was -28. There, let's see what this looks like. The Agilent reported 2.07, so in fact let's call it 2.1 watts, and again it looks as if this microwatt meter is right on the money. So it is working out extremely well. However, there's a couple of things that I need to point out. It didn't just do this right out of the gate. There were several compensations that had to be made, but I was very lucky. Now let me see if I can explain this clearly. There's several different selections on here. I'm using the 0 dBm. In other words, I'm not applying any compensation on this microwatt meter, which is okay, because now let's look at the crossguide coupler. We're testing at 14.25. 14.25 is 40.16 dBm. That's important because 40 dBm is 10 watts. So this is very convenient. On a scale of 0 to 10, based on the fact we've got a -40 dBm input, we could say this scale here is reading exactly in watts, and this is what we need. This is why when I look at it I can say that it's running at 2.05, 2.07, which is where it should be. So this will read, as it stands, it will read up to 10 watts. However, we've got a factor here of +10, so by going to that, we could input up to theoretically 100 watts. The power head may not make it all the way up to 100 watts, but certainly it will make it up to 95. So this is a very flexible device. Again, I prefer my Agilent, but my Agilent cost me $3,000. This would cost me probably less than $1,000 complete with a power head. So if I just wanted a quick and dirty way of looking at power, looking for fluctuations, just looking at approximate maximum and minimum, this microwatt meter would do just the job for me, and I'd be very pleased to have one. That's it. That's all for today.